Hello, welcome to this class of thermal analysis, where we are just seeing the thermal effects on some samples, which can be your solid samples or something else, can be a polymeric sample also. And what we can discuss nicely for your thermogravimetric analysis, what we have abbreviated as TGA, thermogravimetric analysis, and one also we have started discussing is the corresponding derivative one, which is the DTG process. And the nature of this particular sample, that means the sample characteristics is very important. Suppose we have some powdered sample and which is finely powdered. So, the particles what is present and the type of packing both are important. So, what we can see now that if we have two analytes which we want to determine, and these two analytes are, say, if we consider that we want to find the two metal ions, one is calcium 2 plus, another is magnesium 2 plus, and we all know they are very much present in groundwater, in other water samples what we use every day. So, if they are present in water samples and at what concentration level, sometime we define some unit which is parts per million unit, and that parts per million unit if we can apply to some calcium and magnesium samples present in water, that gives us the hardness of that particular water sample. So, if we want to measure the corresponding hardness of these samples, what we can do? We can measure the corresponding amount of calcium and magnesium 2 plus present in the sample as calcium carbonate as well as magnesium carbonate. Now, we want to see if we can have something where we can convert these two from the solution to some insoluble, that means insoluble in water medium, which will be your good precipitate. And whether these calcium and magnesium samples are very useful, what we can use also for standardizing any thermogravimetric instrument. So, if we have the instrument and that instrument has to be standardized in terms of its corresponding change in mass or the weight loss with respect to the temperature change, and how it is standardized for that particular sample, because if we have some well known sample, we know that corresponding weight losses, if we hit these two samples also. So, weight losses if we know, then we can find out the corresponding percentage or the amount of calcium and magnesium present in those samples. So, this as well as something which we can add as the corresponding precipitating agent. So, which is the precipitating agent? The precipitating agent can be C2O4 2 minus, which is your oxalate anion, which has a 2 negative charge, which is the anionic form, dianionic form of oxalic acid or sodium oxalate, what we can use. So, directly we can use Na2C2O4. So, with the bivalent cations calcium 2 plus or magnesium 2 plus, they immediately bind and give rise to the corresponding precipitates of calcium oxalate and magnesium oxalate. So, this one is a different one, where we get that corresponding precipitation of calcium and magnesium can be used for standardization of the instrument, for analyzing the amount of calcium and magnesium present in the sample, and also the weight loss. Characteristics. This is very important. That means, the weight loss characteristic will also be useful to know the corresponding nature of our calcium as well as magnesium oxalate now, because we have added the oxalate anion as the precipitating agent, and that anion is binding to the corresponding cation calcium and magnesium. So, the study will also tell us that we can see the nature of their thermal stability. So, first thing what we can see is their thermal stability, and as I discussed in some of our previous classes, that when we add some precipitating agent and this separation of this calcium and magnesium oxalate takes place from the solution medium, and from the solution medium, if it is insoluble in that water medium or the aqueous medium where we do the reaction. So, in that particular beaker, the solid what is separating out as calcium oxalate. So, these are very fine precipitate. We use this particular technique for gravimetric estimation of calcium also, and that calcium can be present with a solution of say iron 3 plus. So, what we do there, we basically separate out this first, say as the precipitate of ferric hydroxide, which we also write nicely as this. So, this is brown precipitate. So, from the filtrate we get the calcium 2 plus, and then we add the corresponding oxalate anion and we precipitate that. So, if we try to get the corresponding formulation, that means the formula of calcium oxalate, that means the corresponding molecular formula, which can be very useful to know, because the number of water molecules present as water of crystallization is also very important to study, because we have seen that two types of sodium carbonate we can have, the washing soda. When freshly precipitated or freshly prepared sodium carbonate we have, it has 10 water of crystallizations, but if we keep it for longer period even in air, it can lose 9 other water of crystallizations and it remains with that of your monohydrate species, that means sodium carbonate monohydrate. So, the water content, that means water of crystallizations also is very important knowledge or information or characteristics of this particular sample. So, any other solid sample, it can be useful for your other samples like liquid, gas, etc. For if we have a solid sample, it can be a polymeric sample, it can be a cement sample, it can be any other solid sample. So, the information regarding the water content is always very important. Even that solid sample can be your food sample, food materials, or it can be your pharmaceutical samples. So, this water content is always very important, and we want to know when we go for the TG analysis of any of these samples, because at a particular temperature this will go for the water loss, which is the first step, and that we can apply that information as we have discussed earlier in case of drying the precipitate of nickel DMG, nickel dimethyl glyoximate, in air oven So, we should set a particular temperature, and we should know also at what particular temperature we can dry the corresponding sample of nickel DMG. Similarly, this particular calcium oxalate, if we want to go for the corresponding measurement or the analysis based on the drying of the sample and taking the weight, that means the gravimetric estimation, the conventional or the traditional gravimetric analysis can be useful to know about the corresponding amount of calcium oxalate on the crucible or on the filter paper in dry state. So, this thermogravimetric estimation is directly related to the typical gravimetric analysis, and if we put that that means the temperature, the thermometric part, temperature when we add and if we go for the corresponding weight loss of the whole sample, what we find that with regard to the temperature, not only the drying temperature, because this will also give you the drying temperature of the precipitate. So, that particular profile can also give you the species, that means the thermal stability of the calcium oxalate. So, any other thing, any polymeric sample, any cement sample, any ore or any solid or the pharmaceutical sample, we should know its corresponding thermal stability, because we have to keep that particular sample at a particular temperature. If it is unstable at room temperature or at a little bit higher temperature than that of our room temperature, we have to be very much careful about its thermal stability. So, if A is there and with temperature is converting to B, and since in all these cases we are talking about that calcium. So, if we have a compound which bears calcium 2 plus, so calcium bearing one species, then that can be converted to another species, then it can go to another third species, or it can go to the last one, which is another one based on calcium 2. So, these are therefore the conversion of A to D. If we want to measure or if we want to find the corresponding calcium content of the pure solution. So, you can have that calcium present in some pure sample which is in solution, it can be in some solid calcium bearing salts, it can be in ore of calcium or mineral of calcium, or it can be in some cement sample. So, all are these opportunities we can have, and also is n number of things can be there in our body also, in our biological fluids. We require calcium, presence of calcium and its proper assimilation for the corresponding one for a particular process we call is biomineralization. That means, the calcium bearing useful species or the material what we can have in our body, which can also be termed as biomaterials, but the presence of calcium from the food material and its typical absorption can give rise to the corresponding formation of our bone in our body or our teeth or several other useful forms. So, this particular thing, that means calcium is forming A, B, C, D, all these things. So, depending upon their thermal stability, we can start with say calcium oxalate, and the formulation also we do not know, that means what is the number of water molecules present in it, whether it is a monohydrate or a dihydrate or trihydrate. So, we can go for its corresponding Tg plot. So, its Tg plot will give rise to the corresponding plot which is like this. So, instead of labeling all these in terms of the corresponding axis, because this is your corresponding mass loss, we just simply label the temperature. If we start from the room temperature, which is 18 degree centigrade, all will be in degree centigrade, then next is 100, then it is 228, it is 398, it is 420, then it is 660, then it is 838 and so on. So, immediately seeing this particular thermogravimetric plot of calcium oxalate, we see that up to 100 degree centigrade, the hydrate form of the calcium oxalate is stable. That means, if we want to measure the corresponding weight of calcium oxalate in the hydrated form, or if we want to keep that in the hydrated form also, we should preserve that particular sample below 100 degree centigrade, and above 100 degree centigrade monotonously you will have a wet loss characteristics, and that wet loss will continue till 228 degree centigrade. You see, this is a pretty high temperature. Initially it goes this particular one. So, that means the water molecule and the mass loss at this particular point, whether that will correspond to a single water molecule or a double water molecule or triple water molecule, also signifies the number of water molecules present with this calcium oxalate sample. So, what we see that this particular thermogravimetric plot or the thermogravimetric characteristics can give rise to the informations, or it gives us the informations about their wet losses and at which particular temperature which one is stable, and if there is some formation, that means the calcium bearing compound A is going to calcium bearing compound B, going to calcium bearing compound C and calcium bearing compound D. So, before going to that exact analysis, what thermogravimetry tells us, that we just seeing from our previous class, that it determines the mass change of a sample as a function of temperature or time. So, if we have this, that means if we want to measure the corresponding mass change for that particular sample, which is your calcium oxalate, and we will also take immediately that one other one, that means the magnesium oxalate. So, this particular instrument or the technique or the machine will be a good tool for quality control and assurance also. Just now I told you that if we want to use the Tg for our industrially important sample of cement, or the another pharmaceutical industry important sample is your medicine, that means the solid tablets and the capsules, or the solid material or the solid ingredient what we use for making the pharmaceutical samples, because you must have the corresponding quality control and the assurance in terms of the simple presence of calcium ion in water molecule in water samples, or the quality of the cement in terms of the presence of the calcium, that means the percentage of calcium should be known to us in terms of a cement sample, or any other calcium bearing medicine or drug or anything. So, calcium solid tablets can also be analyzed for their presence, and failure analysis of complex polymer mixtures. So, if we have a polymer mixture and that polymer mixtures and blends also. So, polymeric sample, just now I told you also that we can handle polymeric samples also nicely with this particular technique. So, if we have polymer mixtures and blends, and their thermal stability is also very important, because at that particular temperature, whether it is we are using below 50 degree centigrade or we are using that particular sample for the car component, because the car engines and body and all these things, they are having some variable power consumption as well as the temperature rise for their all these components. So, these polymer mixtures and their blends and how good they are. So, for this complex species we can go for the thermal stability analysis, and the failure analysis of these polymer mixtures and the blends will discard them for their useful use. And also we can use this for a variety of chemical processes accompanied by mass change. So, we will just take that example. We have taken this particular example, that calcium oxalate, what we have seen, that a chemical process, that means the thermal degradation, that thermal, we can consider it as a typical chemical process. So, this thermal degradation will accompany some mass change also. So, along with this calcium oxalate, if we take another sample, because both the two metal ions are present in the water sample, so we can precipitate it together, which is your magnesium oxalate. So, this magnesium oxalate when we take and we heat that particular one also in a similar fashion. So, but to a high temperature extent, it will go like this. So, compared to the sample of calcium oxalate, here we see we have 1, 2, 3 breaks in case of calcium sample. In case of magnesium sample, we have 2 breaks only. And if we level these temperatures can be leveled over here. So, this is also the starting point, 18 degree is your room temperature. Then we can reach little bit beyond this temperature. So, it is 176 degree. So, it has good thermal stability compared to your calcium sample. Then this one is in the vicinity of the previous temperature what we obtained in case of calcium oxalate, which is 233 degree. Then we have 397 degree, then 478 degree. Then there is no change beyond that. That means, whatever is formed at this point. So, we have A, then B, then C, and previously in case of calcium oxalate what we have seen, that we can get these 1, 2, 3, 4 samples, that means compound A, compound B, compound C and compound D. And all these, the transformation from A to B, B to C, C to D, all accompanying some mass loss. So, now if we have this axis basically, and now if we just this temperature we can have. So, it will be between these. So, it will be close to 350 to 400 degree centigrade, but these two temperatures are very important. It can be considered as the drying temperature. So, this is our 500 degree centigrade and this is our 900 degree centigrade. So, this calcium oxalate and magnesium oxalate have something in difference such that the thing what we can get for the optimum temperature range, what we can try to find out, where we try to dry or condition this precipitate for gravimetric analysis. So, if we try to get this and if we find that this first wet loss in both the two cases are due to the loss of this water of crystallizations, and we find that this particular dip is much more. So, the mass loss in case of your magnesium sample is more compared to your calcium sample. That immediately signifies that here we have more number of water of crystallizations, which is a dihydrate, compared to your calcium oxalate, which is a monohydrate. So, the calcium oxalate monohydrate is stable up to 100 degree centigrade, whereas magnesium oxalate dihydrate is stable up to 176 degree centigrade. And as a result, these two temperatures if we select, those are the temperature ranges, useful temperature ranges for our gravimetric analysis. So, how do we go for the corresponding thermogravimetric analysis? that what we are looking for? We are looking for a heat we are giving to the sample to get some constant mass, and this particular constant mass is also an important terminology over here, that which particular range you can have a constant mass, as if we have a constant mass in this particular range of 18 to 176, then a constant mass within the range of 233 to 397. That means, whatever sample is formed as compound B of coming from magnesium oxalate is stable in this particular temperature range. And the third one, that means A, B, C, the compound C from magnesium oxalate is also stable in this particular temperature range above 478 degrees centigrade. That means, it is stable at 500 degrees centigrade, it is also stable at 900 centigrade without giving you any mass change. So, the mass will be constant in this range, this mass will be constant in this particular range. So, what we find over here, that if we just simply talk in terms of the corresponding loss of water hydration. So, loss of water hydration will give rise to something where we find that we take the simple sample like copper sulphate pentahydrate. In one of our previous classes, we have just discussed that water present is many more. There are 5 is pentahydrate, we know, that is copper sulphate pentahydrate. If we heat it, so not that all 5 water molecules will go out in a single step, but one is different compared to other 4. So, initially we get the sample which is copper sulphate monohydrate, and we see also the color change. So, that is another indication, good indication of those samples which are colored, unlike your calcium oxalate or magnesium oxalate samples which are white in color. So, this one will immediately show some color change for the monohydrate formation, and then monohydrate will go ultimately to the anhydrous form of copper sulphate, and the temperature ranges which is known to us for the formation of monohydrate copper sulphate and the corresponding anhydrous copper sulphate is important, because some of these samples are very useful. Even they are in small amount, they can show some catalytic thing in any organic transformation, any biochemical transformation, or any pharmaceutical preparations. We can use 3 different types of copper sulphate therefore. And if I ask you to make these 3 samples, how will you make it? When a copper rod or copper copper strings also, or the copper foil is given to you. So, from metallic copper which has been obtained from your ore or mineral of copper, so that can be solubilized in presence of sulfuric acid, and the sulfuric acid we all know that unlike nitric acid, but sulfuric acid some oxidizing power also, which will oxidize this foil to give you the copper sulphate. But if we want to prepare the corresponding copper sulphate in the monohydrate form and the anhydrous form, so this anhydrous form, when it gives rise to all 5 water molecules out, so it is colorless species. And these 2 things, now what we want to see, that the plots we have seen, these are basically the 2 important studies what we can make for thermogravimetric analysis, is the corresponding decomposition and degradation of calcium oxalate to calcium carbonate, and this calcium carbonate to calcium oxide. So, here we see that starting from your hydrated salt, this is hydrated. So, calcium oxalate is also hydrated one, which we just now have seen that it is a monohydrate one. That monohydrate will give rise to the corresponding anhydrous form of calcium oxalate. Then that particular calcium oxalate can break down or go for the corresponding one, where it can, in presence of plenty of oxygen, because oxygen supply if it is there, the another gaseous product which is coming out from this thermal degradation is your carbon dioxide. Otherwise, what we find in absence of this oxygen, or in presence of some inert gas like nitrogen or argon, carbon monoxide can come out. So, that carbon monoxide coming out from the sample of calcium oxalate is a well known fact, and that will give rise to a different kind of weight loss compared to the heating of the sample of calcium oxalate in presence of air or oxygen. So, once this calcium carbonate is formed, because the clinkering process what we know for making cement samples, several carbonates or oxalates and all these things are heated together in the furnace, and we get a very complex structure of these oxides or hydroxides, which can be hydrated or dehydrated in a cyclic manner for all the cement samples. And we all know that this calcium carbonate and all these thing also very much useful for their setting properties. So, this particular elimination of carbon dioxide and all these, not only from your calcium oxalate, but also from calcium carbonate, is very important step to think of, where we can see that the gases which is coming out from those samples, we can also analyze those gases very nicely, that in one case you get the carbon monoxide. So, if the particular thing can be connected to your gas chromatographic analysis or gas chromatography attached to the mass spectrometric analysis, also the GCMS instrument. So, this gas analysis can immediately tell you whether you have the gas which is coming out from heating of the sample is carbon monoxide or carbon dioxide. Similarly, while heating this particular one, so in this particular case, in the second step, we do not need any kind of oxygen for their decomposition, it is directly going out. So, calcium carbonate will be degraded into calcium oxide. We know that the use of calcium oxide, we know that when it is trapping water, we get slack lime and all these things. So, this also can give rise to the carbon dioxide from the particular sample. So, this give rise to a very important information to us, because in detail we will just talk in our next class about the degradation not only for your calcium oxalate, but for the magnesium oxalate also, and that particular degradation process will also tell us about the corresponding stability of these two important compounds, because many number of bivalent metal ions can give you the carbonates. Sometimes it can give rise to the basic carbonates, that means hydroxycarbonates, the copper carbonates, copper hydroxycarbonates, and like magnesium oxalate, several other salts also known. So, all these metal ions can be analyzed by getting its corresponding either oxalate salt or their corresponding carbonate salt. Thank you very much.